Hello students, welcome to lecture number 9. This is a review lecture for the topics of infinite limits and also limits at infinity, asymptotes, both vertical and horizontal, and continuity of functions. I will be briefly reminding you of certain concepts, but the best way to do a review is by solving problems. So we'll have a bunch of problems here today. The first thing I wanted to remind you, this comes up in limits involving infinities. There are limit forms which are actually determinate, meaning you don't need to simplify them. You can always find a value for them, or infinity or minus infinity. But be careful with these in cases of one-sided limits. In the cases where their limits at a point A instead of infinity, you might want to check one-sided. So you'll see what I mean. But I just wanted to mention what they are. When you see something, for example, like 0 over infinity, or even some number over infinity, you might be inclined to think this is indeterminate, that you need to simplify it somehow. But no, this is always going to be a 0. Because just think about it, whatever a number is, if you divide by something that's getting larger and larger, then your expression gets smaller and smaller, which means it goes to 0. And in a similar vein, infinity over 0 or infinity over number will give you infinity, depending now on the sign of this number downstairs, the 0 or the number. We will also see about that. And sums of infinities or differences like this, minus infinity, those are determined. What is not determined is infinity minus infinity, for example. This one is indeterminate. Similarly for products of infinities. So each one of the limits in here will be actually determinate. Calculate or explain why they do not exist. And we're going to start with a very easy one. Item A is 1 over x minus 3. X is going to 3. So this is a number over 0, which means as we compute at least the one-sided limits, we will find a form of infinity, either plus or minus. And to know whether this limit exists or not depends on whether those two one-sided will actually be the same. In this case, if you're coming from the right side, let's say, this is a 1 over 0. X is going to 3, so x minus 3 is going to 0. But this 0 is approached through positive numbers. Okay, x minus 3 is positive if x is on the right side. So this is a case in which it is a plus infinity. You might even want to say something like plus 0 here. Different people use different ways to denote this. The fact that you came to number 0 by looking at positive numbers. Meanwhile, if you're coming from the left side, x minus 3 will now be negative. So it's still a 1 over 0, but the 0 is through negative numbers, which means this is a negative infinity limit. And because those two numbers are different, plus infinity, negative infinity, the actual limit does not exist. So a very easy example right here. Now B, it's 1 plus sine divided by 1 plus cosine. X is going to pi. Well, sine of pi is 0, cosine of pi is minus 1. So when you plug in x equals pi, you get a 1 plus 0, which is 1, over a 1 minus 1, which is 0. 1 over 0. This is number over 0. It is determinate, either plus or minus infinity. You just need to understand if it's going to be a definite sign, or maybe it's a case more like item A, where the two one-sided limits have different signs. But in this case, what is happening to us 1 plus cosine x? Is that always positive, always negative? Depending on the side, what happens? Well, remember that cosine is always between minus 1 and plus 1. Also sine, but we're interested in the cosine here. So if you add 1 to cosine x, this is always going to be larger than or equal to 0. Doesn't matter if you're coming from the left or the right. We don't need to analyze those separately. So, Okay, let me first write down the thing that we already mentioned, 1 plus 0 divided by 1 minus 1. This is a 1 over 0, but this 0 is plus. This limit is plus infinity. Why? If we want to justify this, cosine of, there should have been an x up here, cosine x plus 1 is always larger than or equal to 0. This is true for any x's, not just the x's on one side of pi or the other side. It doesn't matter which x. So in this case, there is a definite sign for this limit. It's plus infinity. Item C. The function is 1 over x over ln of minus 1 over x, and we're going to minus infinity. This now is just a matter of understanding what these functions are doing. For example, 1 over x. As x approaches either minus infinity or plus infinity, 1 over x is becoming 1 over infinity, or minus infinity, but that's always a 0. All right, so at the top, we just have a 0. And what's happening at the bottom? This ln, we're taking ln of minus 1 over x. So again, 1 over x itself is going to 0. But it's a negative number, all right, because it's a minus infinity here. 1 over x is negative, but then we have this other minus sign for it. So you can say this is a 0 but positive. You can say, for example, goes to 0 through positive numbers, which is important because we're taking ln of that. That's the reason why this minus sign is in there. But then what is ln of 0? If this number inside of ln is going to 0, ln of that is going to where? Well, ln of 0 goes to minus infinity. The graph of the ln function looks like this. So you see that as you approach 0 from the positive numbers, ln is approaching negative infinity. But well, you don't even need to know whether this was plus or negative infinity. Number over infinity, it just means 0. It's small number over large number. That gives you a small number, right? So this expression is approaching 0. Very good. Item D now. ln of absolute value of x over x. And x is going to 0. So if you just try to plug in x equals 0, once again, you have ln of 0 minus infinity. And now it's divided by 0. This is one of those where you have a big number divided by a small number. So the answer is big. The answer is going to be infinity. But I'm going to write a question mark here. We don't know, because the answer is infinity, then it matters to know whether it's going to be plus or minus infinity this time. It's different from the previous item where the answer was a 0. 0, you don't care if it's plus or minus, 0 is 0. This one, we need to understand better through what numbers this is happening. For example, right here, the number in the numerator is negative. It's a negative infinity. But the number in the denominator, we don't know if that's negative or positive. It's going to 0. But is it negative or positive? Well, it actually depends on which side you came from, because you have an x right there. So this is a case where you actually need to analyze the two separate lateral limits. If you're going to a 0 from the positive numbers, then this 0 in the denominator is positive. And negative infinity divided by a small positive number is a big negative number. Negative over positive is negative. So this limit is minus infinity. The other one will be plus infinity. By the way, we have an absolute value inside of the ln, otherwise this would not even be defined, right? Without this absolute value inside of the ln, you cannot go towards 0 from the negative side because you cannot take ln of x. But with the absolute value, that's fine. And you can see here the 0 in the denominator now is through negative numbers. Negative over negative gives you positive. So you have two one-sided limits which are different. So I'm going to erase my initial guess here, the one with the question mark right here. I'm going to actually give you the answer. It does not exist because of the next two lines. That was our item D, and the last one is, okay, 2x cubed over 3x squared plus 1. And then plus 4x squared over 6x plus 1. This is a limit of a sum. We know that the limit of a sum is equal to the sum of the limits as long as that gives you a well-defined expression. And this is actually going to be the case in here. Remember, we're talking about determinate forms. Just think about what happens to each one of these individually as x is going to negative infinity. Each one is a rational function. So you know that the highest degree terms are the ones that are going to determine the behavior here. In this case, both expressions have a higher numerator than denominator. The x is determining what happens. But how do we know that for sure? We're going to be dividing by x, which is the highest degree in the denominator in each one. So I'm going to write that this is equal to dividing by x, 2x squared over 3 plus 1 over x, and then plus 4x divided by 6 over 1 plus x. This was a square right here, I think, which would make sense. Let me correct this in red. This denominator here was 3x squared. So that means 2x should have been the numerator here, and then just 3 here. I hope this is clearer. Sorry about the mistake, but yeah, this is now a good expression right here. What happens as x goes to negative infinity? In the first one, 2x is going to negative infinity. 3 is going to 3, 1 over x is going to 0. And the other one, 4x is going to negative infinity. 6 is going to 6, 1 over x is going to 0. So you see this is negative infinity minus infinity. So negative infinity plus negative infinity. This is determinate. Two negative infinities make one negative infinity. That was the point of this problem, to show you that you can compute each one separately in this case. How likely are you to find this one in an exam, for example? Unlikely. Usually the exam problems will be indeterminate forms, but I wanted to start with these ones today. Okay, scrolling back up just to double check. All right. Now let's talk about the indeterminate forms. These are the indeterminate forms: 0 over 0, infinity over infinity, 0 times infinity, or also the sum of infinities of different signs, like infinity minus infinity. Those are indeterminate. They could be anything, or they could also not exist. You are only going to know after you simplify, which means factor and cancel, rationalize, whatever you need. Now, the very first example here is the same as the previous item, but now I have a minus. Now this is going to be an indeterminate form. Remember, both of these are minus infinity. So with this extra minus here, you have minus infinity plus infinity. That's indeterminate, which means we have to simplify it. So let's start with this A. How do we simplify this difference of two fractions? I'm going to take a common denominator. So I'm going to multiply the two denominators. 18x cubed plus 3x squared plus 6x plus 1. And the numerators will be like this: 2x cubed times 6x plus 1 minus 4x squared, 3x squared plus 1. Let's simplify this. The 2x cubed times 6x will make a 12x to the fourth. But this is also going to be a minus 12x to the fourth right here. So those are going to go away. You're only going to be left with 2x cubed from this first term minus 4x squared from the other term. And what happens to this limit now? X is going to negative infinity. So we know that the terms of higher degree will be determining what happens, and they are of equal degree now. It's a cube. So we know what the answer is, right? They're determined by the ratio of these coefficients, 2 and 18. But how do we know that? It's again by dividing both numerator and denominator by the highest degree term of the denominator, which is x cubed. So after you do that, you will see this expression showing up, which is now an expression for which you can plug in x equals negative infinity. Doesn't really matter what the sign is, because number over infinity is 0. So you really just have 2 over 18, which is 1 over 9. So this item A was an example of a limit at infinity being equal to a finite number, 1 over 9. B should be very easy. Probably fits in here. We can do that like in here. X is going to negative 3. If you try to plug in negative 3, you will see a 0 over 0. That's how you know this is indeterminate. I should always start by mentioning that, of course. But how do we simplify this one? I hope you know. The x squared minus 9 in the numerator can be written as x plus 3 times x minus 3. The x plus 3 will go away. And now you can plug in negative 3 in the expression x minus 3, giving you minus 6. This one is actually a finite limit at a finite location, which could happen even in an exam about infinite limits. It's not clear just from looking at the expression what it's going to be. And in this case, it gave us an actual number. Look at item C now. It's the same function, but what changed was the location of the limit. It's now a limit at infinity. It's x squared minus 9 over x plus 3. Fits in here. That's an example of where, because x is going to infinity, x is large, then what determines the behavior here is the behavior of the degrees. In this case, the numerator has a higher degree, so we expect to find the limit of infinity in this case. And how do we know that? You simply divide by x, which is the highest degree of the denominator. So after doing that, this is the expression you get: x minus 9 over x divided by 1 plus 3 over x. You can plug in infinity in here now. This gives you infinity minus 0 divided by 1 plus 0. So infinity over 1 is infinity. This is an infinite limit at infinity. And finally, D, x over root 3x squared plus 7. X is going to negative infinity. Thinking about degrees here, the degree in the denominator, the dominating degree is also x because of the square root. It's not like we are distributing the square root under each term separately. That's incorrect. But rather, as x grows in size, the first term is the one that dominates. The others become irrelevant. So that term dictates the size of that expression. But how do we actually find this limit? I'm going to factor an x squared from the well, think about it this way. I'm going to divide both of the terms by x. So x over x is 1. Let's leave the 1 over x in the denominator like this. We know that this 1 over x is going to cancel the x squared inside of the square root somehow. I'm going to factor now the x squared from inside of the square root. 3 plus, sorry, x squared times 3 plus 7 over x squared. And now you can see after you take the square root of x squared, that's the expression that you need to always be careful about. Let me write it like this. The square root of x squared is not x, it is absolute value of x. Don't forget that, which means in this case, because x is going to negative infinity, x is a negative number. Absolute value of x is actually equal to minus x because x is negative, so then minus x is positive, right? And then this minus x divided by this other x in here, together they make a negative 1. This over this give you a negative 1. So the simplification here works like this: minus root of 3 plus 7 over x squared. All right, what is this? Well, x is going to negative infinity. This time we can actually plug in negative infinity in the 7 over x squared term, just becomes a 0. So this is your final answer here, 1 over negative root 3, which, by the way, there are many ways to write this. If you rationalize, if you bring the negative outside, but as long as you got the right answer, this should be fine. So this is a finite limit at infinity. Now, because we're talking about infinite limits or limits at infinity, this brings in the topic of asymptotes. I have a brief reminder here. A vertical asymptote of the equation x equals a. This happens when you have a infinite limit at a finite location. It could be a limit like this. It could be just a lateral limit like these. But as long as you have at least one plus or minus infinity in a location like that, then you have this vertical asymptote. Horizontal asymptotes, you can have at most 2 of them. A horizontal asymptote of equation y equals L is when the number L is a limit, either at infinity or at minus infinity. That's why you can only have at most 2 when these 2 limits are different. And we also briefly discussed slanted or oblique asymptotes. We don't really need to know this for our exam, but just so you know, it's interesting, it's useful to remember. And a line of equation y equals cx plus d is an asymptote when, if you take the difference between the function and the line, and you look at what happens as x grows large, either plus or minus infinity, you find a difference of 0 in the limit. So this basically means the function is getting closer to the line. That's how we check for slanted asymptotes, but we actually haven't done much about this, and you don't need to worry about this concept. We'll be focusing on vertical and horizontal. Okay, so here we have a problem about vertical asymptotes. I realized I had a typo in my f of x function, so I covered it in here and I included a new definition here. Let's get right into it. Finding vertical asymptotes, the initial work that you have to do is determining where are the limits that you need to compute. And the answer is, for a vertical asymptote, that it can only happen in places where the function is undefined, or like if the domain is just one interval, then at the extremes of that interval, those are locations where your function, let's say this was the definition of it, the locations where you can possibly have a vertical asymptote like this. So you just need to understand what those locations are. For example, looking at this f of x, looking at the denominator here, what are the places where it could be a 0? Having a 0 in the denominator is the only way in which you can have an infinite limit, right? So if you factor this denominator, you can see that this is a x minus 1, x minus 3. So only at the points x equals 1 and x equals 3 can you have a limit of infinity or minus infinity, but not necessarily. It's not necessarily the case that just because you have these guys in the denominator that you're going to have asymptotes there, because it also depends on what you have in the numerator, which in this case is also very easy to find. X minus 1 times x minus 2 gives you that. Yeah, I hope you can see the function right here, by the way. So this is your f of x. The expression of the function itself is this, and you cannot cancel it out at this stage, because you don't know what this x is at this stage. If you're just saying what f of x is, if x is 1, for example, then you cannot say this cancels with that because x minus 1 is 0. So rather f of 1 is undefined. But this tells you that 1 and 3 are the locations where you can have possibly asymptotes. You just need to check if that's actually the case. What happens if you go, for example, towards 1? Let's say from the right side, you should check both sides, because as long as you have a limit, infinite limit in at least one of them, then you know there is an asymptote. But what happens in here? Now, okay, if you are calculating a limit, then you're going towards 1, but you are not at the number 1. Then that means you can actually cancel the x minus 1 factors when calculating this limit. And well, this gives you a finite number, actually. Turns out to be minus 1 over minus 2, so 1/2. But you don't really care about the number, because you found out 1/2 here and not infinity. Then, well, at least we know there is no asymptote coming from this side, but actually the limit from the other side is also not going to be infinity. It's exactly the same calculation, right? Turns out you do not even need to analyze both sides separately. This limit exists, it is 1/2. So there is no vertical asymptote at x equals 1. But the other one that we needed to analyze by looking at this denominator right here is x equals 3. Let's see what happens. Well, okay, what is going to happen when you plug in, let's say we're going towards 3 from the right side. This is going to be one of those cases of number over 0, which gives you either plus or minus infinity. I'm going to actually find the plus or minus because, well, why not? So plug in 3 here. Let's write plus 0. X minus 3, if you're coming from the right side, is a 0 through positive numbers. So number over 0, where that 0 is positive, a positive small number, it means plus infinity. But regardless of which sign of infinity we found here, because we found an infinity, we know there is an asymptote at this number. We don't even need to know the other limit. X equals 3 is a vertical asymptote. And it turns out from the other side, the function has a limit of minus infinity. Okay, so if you wanted to graph this function, it probably looks like this. Around the number positive 3. From the right side, it has a plus infinity limit. From the left side, a negative infinity. And then at the number 1, it's actually undefined, but it has a limit of 1/2. So it goes through that line with an open circle, through that point with an open circle. The graph tends to that open circle, but there is no value of f of 1. All right, but this is the only vertical asymptote here. Now we can move on to item B. B is g of x equals ln x plus 2 minus 1. Okay, what are the only possible places where you can have asymptotes for this function? Vertical asymptotes, places where it's undefined. but not just undefined, but like close to places where it is defined so that you can take limits. In the case of the ln function, that's only around 0, right? If it was more precisely, only for x's such that the thing inside of ln becomes 0. In that case, x equals -2. So the limit as x goes to -2, we have to understand at least one of these guys, either the limit itself or the right side or the left side limit. In this case, only the right side limit is well defined. If you're coming towards -2 from the right, that makes this number x plus 2 positive, which it has to be if you're taking a ln of it. So this is the only limit that you can actually compute. And what is it? Well, when x goes to -2, x plus 2 goes to 0, ln of 0 goes to -infinity. You have -infinity minus 1, which is just -infinity. But because it is a form of infinity, there is an asymptote there. X equals -2 is a vertical asymptote. It's the only one, actually, because there are no other places where there could be an asymptote. Thinking about the graph of this function just for fun, just so we understand what's happening, the ln function is just translated 2 units to the left because we are adding 2 to x. And it's also translated 1 unit down, but that's really not going to change it much. So it's looking like this. Actually, the function add 0 should have been negative, but whatever. The important part is right here. The fact that it's approaching a vertical line, that at the only location where it could do that. So that's a vertical asymptote. Now let me scroll to the last one. H of x equals e to the -1 over x. In terms of the exponential function, there is nothing problematic about it. Whatever you can plug in the exponent here is going to give you a valid number. But we do have a quotient in there. We have a 1 over x. So the problematic points for this function are x equals 0. That's a possible location where you can have an asymptote. That's where you want to analyze limits. And what is going to happen with these limits, actually, it will matter to understand if they're coming from plus or minus. Let's see why. What is going to happen to 1 over x, or -1 over x, let's say, as you come towards 0 using positive numbers? 1 over 0 gives you infinity. If x is positive, because of this minus outside, this will be a -infinity. All right, and this is e to the -infinity. What it means is the limit. So the proper way to say this is that limit of e to the minus, let's say u, as u goes to -infinity. But you can also write e to the -infinity. That's a 0. We should know this from the graph of the exponential function, for example. So in principle, we don't find an asymptote here according to this limit because we found a finite value. But what's going to happen with the other limit, going towards 0 from the left? Well, 1 over x is still a form of infinity. It's 1 over 0. But is it this time x is negative? So it's -infinity for the 1 over x, but we also have a minus outside, making that a plus. So you can probably say that, I think I had a mistake in the previous one. Proper way to write this would be u going to -infinity with a minus u here. Yeah, just think about the minus. I just want to clarify this notation that I'm doing. I'm basically saying that the 1 over x is my new u. So this minus outside of the u is the same from the original function. But when x was positive, this u was going to plus infinity. But now that x is negative, this u is going to -infinity. All right. That's the difference here. And what is this limit now? If you're taking u to minus infinity, and you're doing e to the minus u. That means e to the plus infinity, which is infinity. And that's what we care about. We found an infinity value. That means that there is an asymptote there. X equals 0 is a vertical asymptote. Only because of one-sided limit, not the other. Next, let's talk about horizontal asymptotes. Again, I have 3 functions in here. We want to find them, if any, if they exist. Horizontal asymptotes are easier to start. What do? You just find the limits at plus and minus infinity. That's all. And if they are numbers, then you have asymptotes. So this is literally a question of finding limits at plus or minus infinity for both of for all of these functions here. Now the f function, you see f has, if you try to plug in infinity in f, you get a problem. You're going to have like infinity over infinity. So you need to simplify this somehow. And you also see in the denominator here a difference of terms where at least one of them involves the square root. So the most likely trick to succeed here will be the rationalization trick. Like this, multiplying and dividing by this term with the plus. Now, you probably don't want to, at this level, distribute out the numerators here. You can leave them indicated like this. 2x minus 1 times 3x plus the square root. You should at least do the denominator first to see what's going to be the simplification. The difference of the squares will be 9x squared minus x squared plus 2, which simplifies down to just 8x squared minus 2. Let me erase this and write the simplified version. 8x squared minus 2. What are we going to do with this? Well, we still need to do some form of simplification. It's usually the case that the term that does not have the square root in the numerator in this case is the one that's going to simplify with the one downstairs. This is also the case in here. You just have to realize how 2x minus 1 is a factor of the downstairs. The first thing that you can try is factor this number 2. Let me do that. And what is 4x squared minus 1? This is a difference of squares. This is 2x plus 1, 2x minus 1. So there you find it. The 2x minus 1 was hidden in that term. We're going to cancel that. And what does that leave you? Just 3x plus square root of x squared plus 2 divided by 2 times 2x plus 1, which we can probably distribute now. Well, let me write this. Okay. Well, this is still going to give you infinity over infinity if you plug in. I'm going to distribute the 2 in the denominators so we can see more clearly what's happening, but it really doesn't help you much. 2 times 2x plus 1. This is basically a quotient of linear functions in the limit because of the square root of x squared. This is also a term of size x approximately. So that's our next step. Our next step is going to be to divide everything by x. How do we do that? With the square root. Remember, I usually like to leave the x outside like this. You know that it's going to cancel with the x squared inside. So I'm factoring the x squared inside of the square root. Now, once again, we have this trick of the square root of x squared. In this case, it's going to be just x because we're going to plus infinity. So after bringing this x squared outside of the square root as just x, it goes away with this other 1 over x here, giving you a plus 1. And you finally have an expression for which the limit can be computed. What is it in this case? Plug in infinity into the 2 over x and the 2 over x squared. Those are all 0. So you have 4 over 4, which is 1. A finite number. All right, so that means y equals 1 is an asymptote, a horizontal asymptote, I should say. Okay, now we're halfway done with this item. We were looking for the horizontal asymptotes. We just found one from the limit at plus infinity. We need another one for minus infinity. But if you think about it, most of the simplifications are all the same here. What happens with the limit at minus infinity now? You would start the same way. You would still do this cancellation right here. The only place where you're going to find something different is right here, when we brought the x squared outside of the square root as x, because it was x going to plus infinity. Now, if you're going to minus infinity, that gets a minus sign. Square root of x squared is minus x. So you can write, for example, like this. Now, if you want to go to minus infinity, after all the same steps, what you find now is right here, 3 minus the square root divided by 4 plus 2 over x. So you see that when you plug this in, you're going to get 3 minus root 1 over 4 plus 0. This time, this is a 2 over 4, or 1/2. Different limit at minus infinity caused by this. This is usually how you get a different value for the limit at plus and minus infinity. This old trick of the square root of x squared. All right, so the y equals 1/2 is another horizontal asymptote. That was the f function. G is going to be easier. Probably fits here. Item B. What is the limit? For example, as x goes to minus infinity, g of x. Remember, we're looking for horizontal asymptotes. We need both limits at plus and minus infinity. This one, think about it for a while. It does not exist. Remember, you cannot take ln of a negative number. If x is going to minus infinity, 1 over x is also negative, and ln of a negative number does not exist. So there you have it. But what about plus infinity? Now, what happens to this expression as x is going to plus infinity? 1 over x is going to 1 over infinity, which is 0. So in informal language, you might say this is equal to ln of 0, which is negative infinity. This is informal, by the way. It's acceptable in a calculus course to say that it's equal. It's not really equal, rather the limit is negative infinity. But yeah, we should know this, again, because of the graph of ln. When you approach 0 from the positive numbers, let's say, yeah, that should have been in here like plus 0, then you're going towards negative infinity. Let's do it this way. All right, so again, this limit does exist, but it's not a number. It's negative infinity, so there are no horizontal asymptotes. And we're gonna do h down there, h to the x plus 2, h to the 3x plus 5. Finding the two limits for h. The limit at minus infinity does not give you any trouble, actually. Think about it. E to the x, once again thinking about the graph of the function, it starts out at 0 when x is minus infinity. Here's the graph. Either e to the x or e to the 3x, also e to the ax for any positive x, looks like this. So you can actually say the limit of e to the x here is 0 when you're going to minus infinity. The limit of e to the 3x is also 0. And you have a number, 2/5. Because you have a number, you have an asymptote. Y equals 2/5. What about now at plus infinity? Now you have a problem if you try to plug in, because both e to the x and e to the 3x will go to plus infinity. Infinity over infinity is now indeterminate, which means we need to simplify this somehow. The best way to do this is by dividing by e to the 3x, which you can consider the highest degree term in the denominator. What happens if we do that? So basically, dividing by e to the 3x is the same thing as multiplying each one by e to the minus 3x. What happens if we do that? E to the x times e to the minus 3x is e to the minus 2x. And downstairs here, you're going to have 1 plus 5 e to the minus 3x. What happens? Now you can plug in e to the minus anything when that thing is going to infinity is 0. So you have mostly zeros here except for the 1 in the denominator. 0 over 1 is 0, which means now we found a value, we found a finite value. So this is an asymptote. So once again, we have a function with two different horizontal asymptotes. All right, now let's talk about continuity. I've mentioned there are three different conditions for continuity at a point, but really you should only think of them as one. This last one kind of implies the other two. They basically say the value exists, f of a, and the limit as you approach that value also exists. But then we finally say those two numbers must be the same. So I mean, just by saying the third one, you kind of implying that those numbers exist. All right, this is what continuity is. It relates a limit to the value of the function at the point. So for example, consider this function here, piecewise 4 pieces. What is the domain? What are the points where it's discontinuous? And we'll talk about C later. Those two should be easy, the first ones. What is the domain of this function? What are the places where it is defined? It has a value for all negative x's. Then all x's strictly between 0 and 1. Notice that we skipped 0. There is no value for x equals 0. Then we do define it for numbers between 1 and 5, and 1 is included. 5 is not included here, but then 5 is also not included in the next one. And everything larger than 5 is included. So just from looking here, we see that f is undefined at 0 and 5. The domain is everything other than those two numbers. So the domain in interval notation, you need to have an interval that stops at 0, then picks up between 0 and 5, and then goes from 5 onwards. Right? You don't have to stop at the number 1, for example, like this 0 to 1 excluded, and then 1 included to 5, for example. Well, the union of these two pieces is the same as this piece between 0 and 5. So you don't have to write it this way. Although it would also be correct. This is a domain. Now, what are the points where it's discontinuous? 0 and 5 are points where f is discontinuous. Simply because it's not defined at those numbers. So we knew that already, that continuity requires f of a to be defined. But there might be also other points where it is discontinuous. In the case of a piecewise function like this, where each piece is a continuous function, that can only happen at the places where it breaks, like 0, 1, and 5 in this problem. So we already talked about 0 and 5, but what about 1? How do we know if it's continuous or not at this number 1? Well, we have the definition on either side of 1. We just need to know if they meet or not. So in other words, we need to understand, is f of 1 equal to the limit of f of x as x approaches 1? Or rather, does the limit even exist to begin with? Just looking at this expression, I don't know. We have to compute this. But this is a very easy one to do. What are the limits from each side? If you're coming towards 1 from the right, then you are right here in the expression between 1 and 5. The expression is just x minus 2, giving you a limit of -3. No, sorry, 1 minus 2 is -1. Whereas if you're coming from the left side, so x is smaller than 1, but close to 1, then the expression will be 2x plus 1, this one. 2x plus 1 if you are between 0 and 1. What does this give you? 2 times 1 plus 1 is 3. They are different. So no, the f of 1 is not equal to this limit. It doesn't even exist, the limit. Which means the function is also discontinuous at 1. And this answers the question. What are the places where it is discontinuous? 0, 1, and 5. And now we can move on to C. Let me scroll up to read that. For each point A you found in item B, so those numbers 0, 1, and 5, determine if it is possible to change the value of f of a or assign a value if it doesn't exist in such a way that f becomes continuous. This is a common type of problem. You have a discontinuous function at specific places, but then you want to ask, can we extend the function in a continuous way, or maybe change the values to make it continuous? So for example, look at the number 1. The one-sided limits around the number 1 actually did not exist. Remember, I mean, they existed, but they were not equal. So the limit itself does not exist. This means that no matter what you change the value of f of 1 to be, you will never get this condition here that it's equal to the limit, because the limit does not exist. So starting with this number in C, impossible to, let's say, fix discontinuity at 1. At, let's say, a equals 1. This is because this limit did not even exist. So whatever you choose to be f of 1, it's still going to be a discontinuous function. So we need to analyze what happens in the other points, 0 and 5. Again, scrolling back up. What is happening at 0? We don't have a value for f of 0. We want to know if it's possible to create one. But look at the one-sided limits. These are the two expressions for f around 0. What are the limits? The one-sided limits as it goes to 0. The first one will give you a 0. The second one will give you a 1. All right, let's write this down. Just from looking at the expressions, the one-sided limits for 0 are also different. which means that the limit does not exist. So for the same reason as for the number 1, it's again impossible to fix. Impossible to assign a value for f of 0 to make f continuous at 0. Because this limit will not exist anyway. Now the analysis at the number 5, I'm scrolling back up again. This is going to be a different one. What happens around the number 5 with the one-sided limits? From the left, you're going to get a 3. From the right, you're also going to get a 3, right? 13 minus 2 times 5. Looking at this expression. So I'm not writing the calculation, but I hope you know what I mean. The two one-sided limits are equal to 3. So the original function does not have a value for f of 5, but if we assign the number 3 for f of 5, then f will be continuous at 5. This is what the question was asking. Only at this number 5, it was possible to fix the discontinuity. So, all right, this was this question. Let's move on to the last one. Also a very common type of question for continuity. A piecewise function with breaks. What are the values of the parameters a and b? You can see the function has a and b in it. What are the values of those that make this function continuous everywhere, which means at all points? Oh, well, what do we need to understand is the only possible places where this function is discontinuous are 1 and 5. Again, the places where the definition changes. But it might still be continuous at those points when the one-sided limits coincide to the value of the function. So for example, the one-sided limit, let's say from the left as you approach 1, well, if you're looking at x less than 1, you're looking at the expression 2ax plus b. This is going to be a 2a plus b. I'm plugging in x equals 1. Whereas if you're coming from the left, sorry, from the right, then you want to use the expression ax squared plus 2. That's what the function is if x is larger than 1, but close to 1. And this limit is actually equal to a plus 2. You need these two numbers to be equal to each other and also equal to f of 1, but well, f of 1 is already one of these two numbers. According to the definition, f of 1 is 2a plus b. Okay, it's the expression that you get when you plug in x equals 1 in the first piece. Because of this less than or equal here, that's how I know. So as long as the two numbers are equal to each other, you're going to have continuity at 1. By setting them equal to each other, you have an equation that relates them. We can simplify this to like a plus b equals 2. That's a relationship between a and b. We cannot find a and b just from here. It's one equation for two parameters. We're going to need some other equation if we want to find them. But we know how to get it. It's the same principle now at the other two pieces. And the number 5, which is where they switch roles. So let's do that. What is the limit as you approach 5 from the left? Then you're looking at the expression ax squared plus 2. Plugging in x equals 5 gives you 25a plus 2. Meanwhile, the other limit If you are to the right side of 5, the expression is actually bx squared plus 27. And this is a 25b plus 27. Those two one-sided limits need to be equal to each other. One of them is f of 5. I think it was the second one. Yeah, look at this. F of 5 is given by the second expression with x equals 5. So f of 5 is already the second one. If the first and the second are equal to each other, then you have the continuity conditions for 5. So you set those equal to each other. Let's move the b to the left and the 2 to the right. 25a minus 25b equals 25. Obviously, I want to simplify this down to a minus b equals 1. Those are the two equations you needed. Now this is a linear system. A plus b equals 2, a minus b equals 1. It's a very simple one. Think of this however you like to solve linear systems. Probably the easiest solution here is to add the two. You're going to get to a equals 3 halves. And just substitute this into one of the equations like the first one. 3 halves plus b equals 2, b equals 1 half. Those are the values of the parameters that make this function continuous everywhere, continuous at both points where it looked like it was going to be discontinuous.